Okay. Yeah, I believe we were supposed to give a brief introduction, so I'll start with that before I go into the content of the talk. So yeah, my name's Steven. I'm a sixth-year PhD student working in Jeff Neaton's group. We're also a computational or theoretical group. Definitely some level of collaboration with the Pearson group, but unfortunately I don't have the pleasure. Yeah, today I'll be presenting some work that we've been doing on studying basically like optical interactions in materials, and specifically try to understand how the lattice dynamics will affect those optical excitations. And maybe unlike the high throughput thing, I'll be talking about just one material for basically the whole talk. So it's kind of a difference in focus of theory. So that's kind of a cool contrast, I think. Yeah, so maybe I'll just hop in here. So the basic idea of what I'll be talking about today is that when you shine light on a gap material in the optical range, you will basically excite an electron into a conduction band, and you'll have this hole that's left behind in the valence band at whatever the frequency of that gap that you're exciting is. And so, this is like the very basic picture of optical excitation. And the first thing that we could do as a way of trying to model this, a refinement on this, is to think about what happens when you have this electron and hole in a material. And kind of the very basic intuition you can say is that, well, these are two particles of opposite charge, and they're going to interact with each other by some kind of Coulomb interaction. And we can map this onto a problem that many people who have done quantum mechanics have had to solve at one point, which is the hydrogen problem. It's a slightly different version of that problem here in that we are not in a vacuum, we're in some kind of material. So the Coulomb potential is screened by this dielectric constant here. And then the picture of what we call the mass of the electron and hole is a little bit different because it's inside of material. So these are like dressed particles. So you have kind of an effective mass and an effective hole, and then an effective reduced mass. But taking all that into consideration, it's ultimately still the same basic type of problem. And so what you end up with here is basically the solutions to the hydrogen atom, but instead you have this dielectric constant and this effective mass that give you a slightly different picture. But that's not too important for what I want to get into. The main point is that there is some kind of bound state that forms when you create this type of excitation. And that bound state lowers the energy required for that excitation by some amount. And so colloquially, or like within the community, we call these things excitons. And they have some kind of binding energy, EB. OK, so this is like a very simple picture that was developed quite a while ago by Wanier and Mott. But we can do better. So as computational physicists, what we'll do to try to tackle this problem is a little bit more of a rigorous formulation of this, known as the Bethe-Salpeter equation, which is, I won't go into any detail here, and don't get scared by the math. But I just want to say, this boils down to an eigenvalue problem, that we basically have these non-interacting electron-hole pairs represented by this diagonal matrix element here, and then we have all the ways that these can interact with each other with this other matrix element here. And so there's been a lot of pioneering work in this Bethe-Salpeter equation and solving it from first principles by Steve Louie and others. And the basic idea is you refine this very simple, like 1 over Coulomb potential 1 over R with the epsilon screening to include a full dielectric constant of the material, which depends on frequency and momentum. It's a much more comprehensive picture. And you include this inside of these mixing matrix elements here. But notably, what I want to say about this is, this is, as written here, kind of including electron-electron interactions and the screening that comes from that. It's notably neglecting what happens when these electrons are inside of a lattice and how the lattice responds to those electrons and holes, which will also have a screening effect. But under this approximation, you can solve this. You can get these eigenvalues out of it, which basically give you the frequencies where an optical excitation can occur in this new picture. And using a Fermi's golden rule approach, you can kind of assemble all of the possible optical matrix elements and then weight them by wherever they occur in the frequency space, add all these up. And when we say add up delta functions, what that really means is make it some kind of Gaussian and throw them all together. And what you can do is you can get some kind of optical absorption spectra, this here being the imaginary part of the dielectric constant. So in short, how the material absorbs light based on the frequency of light you're shining on it. And so this is great, and you can do a lot of really cool stuff with this. What I want to talk about specifically here is maybe a case where this doesn't work as well as we would have hoped. And that's the case of this material called bismuth vanadium oxide. But as we'll kind of get into it, it's more of a general problem. But I ran into this material when I was doing some calculations a few years ago on this material, where we found basically that the theory predicts this massive peak here at the onsite of the spectra. This would be what I was referring to as the exciton in this more advanced treatment here. But then when we look to experimental measurements of this, they really don't see anything that looks like that. And so what's going on here? So the basic idea that I want to drive home is that this is actually due to lattice screening effects. And so just as like a kind of animation to motivate this, when we look at a material like bismuth vanadium oxide, it has these different normal modes in which the lattice can vibrate. These are often called phonons. And then basically what we want to do is to figure out a way to include these types of interactions from these phonons and how they also screen the electron-phonon interaction. And so for anyone who's kind of a fan of many-body perturbation theory or trying to diagrammatically solve these types of things in materials, I don't know how many of those people are in here there are, but when they originally wrote down these equations for trying to understand the screened electron interaction in materials, basically around the exact same time, they wrote down equations to just try to describe what happens because of phonons. But it's a much harder problem to tackle, and so people haven't really been trying to address this ab initio, like from first principle calculations, until really like the past couple years. And so I want to at least give credit and shout outs to a lot of my collaborators here who have been kind of paving the way on this. So a few years ago, Marina Phillip and Jonah Haber, both former Newton Group members, developed at least some level of modeling this that can be system specific, where you can basically plug in some things about the phonon frequencies in the material and the exciton binding energy, and you can get how much the exciton binding energy will be affected by these screening effects. And then much more excitingly and more recently, Antonio Alvertis and kind of all the rest of these guys as well developed like a first attempt at trying to actually solve this from first principles for basically whatever material you want. And then also Christopher specifically has been really focusing on how to understand the lifetimes and the types of effects that can occur, decay effects that can occur as a result of this interaction. So I stand on the shoulder of giants, but basically what I've been working on is extending this to complicated systems and really beefing up the calculations to look at something where the interactions due to this are much more interesting. So one thing I'll note about a lot of these previous studies is that the effects on the exciton binding energy is basically these screening effects will slightly reduce the binding energy. It'll push it up maybe 10 or 20%. And this pushes it closer to experimental agreement. It tends to be that the Bailey-Salpeter equation will overestimate how much an exciton will bind, and it'll kind of have this exciton peak shifted a little bit more than it should be. And so these corrections are pushing it in the right direction, but what we really wanted to see was, is there a case where this is like much more dramatic? Okay, so I'll also just show a brief bit of math here, and I won't go into any detail specifically, but this is the phonon kernel that we're talking about, phonon interaction kernel that we're talking about here. So these basically are how the electrons and phonons interact, and then you have these propagator-like terms. And these actually play an important role here, which I just want to draw a tiny bit of attention to in a second. So what can you do with this? Okay, so what does this do? Well, basically, it'll renormalize the exciton binding energies by whatever the real part of this matrix element is once you solve it. And then also, the imaginary part that you get out of this will give you an understanding of how your states will decay. And then one thing I want to note here, and why I've kind of written it out like this, is that one thing that plays an important role here is that actually what frequency you plug into this kernel actually plays a very important role. And this is actually not the case in the previous electronic one. So this is one of the reasons it's a more difficult problem, is you have to kind of solve this frequency-specific problem. But one of the consequences of that is that basically because you can have these dynamical effects in the denominator of this propagator-type term, you can actually see decays happening in your system. Like an exciton can form and then decay at some later time as a result of this type of interaction. So just to give you a picture of what that might look like, I might form an exciton, and then as a result of these interactions with phonons, I could actually then emit some lattice vibration and scatter the electron in holes to different parts in the band structure. Okay, so I'll present results on this in 1 second, but I wanted to at least provide a tiny brief introduction into why we're doing this for bismuth vanadium oxide. So this is often known as a complex material. It's kind of very famous for its favorable photocatalytic properties. So you shine light on this, and it's good at catalyzing things. You have lots of oxidation possibility. Hint, hint, maybe the electron and hole are kind of splitting apart in a way that's favorable when you shine light on this. And we're looking at the monoclinic phase. And so I think I'm just going to skip through this, but the bands are relatively flat, and the phonon spectrum runs from about 0 to 100 MeV. Okay, so what's the basic picture here? So when we include no phonon interactions, the exciton binding energy for this material is just under 100 millielectron volts. And then once we include this phonon interaction kernel, we see just a dramatic change in what the exciton binding energy is. So even at 0 temperature, we're seeing that it gets nearly cut in half. And then once you go to higher temperatures, things kind of get a little crazy, but maybe just the 2 points to drive home are, one, the excitonic state is now sitting above where the regular band gap the original band gap was. And two, I've tried to plot on here basically this line width, so this represents 2 times the imaginary part of this interaction term. So the general idea here is the wider this line width is, the more likely the state is to decay. So yeah. Oh, and I wanted to note here that although you can't quite see it, and I'll get into this more detail in a second, but there is actually a finite line width even at 0 temperature. And as far as I can tell, this might be the first reported case of exciton decay at 0 temperature, which is super cool. More on that in a second. But you'll also notice as temperature goes up, there's kind of some dramatic shifts here, especially in the line width. It kind of grows dramatically. And we can attribute this to basically as the temperature increases, the binding energy further decreases, and that changes this energy denominator of that previous expression and opens up new pathways, new channels for things to decay. So basically the message here is that as you're increasing the temperature, more and more things can decay, and the dynamics get very interesting. And so yeah, as we see, once we reach around 300 Kelvin, things are just totally different. You have this state that's massively renormalized with an extremely short lifetime. Okay, so now I'll talk about the lifetime specifically. So we can also look at that line width and then basically look at 1 over that to get a lifetime. And we can see here at 0 Kelvin, the line width, or the lifetime is about 6 picoseconds. It's a fairly reasonable number for experiments to maybe be able to observe this. But then what's notable here is as you increase temperature, you very quickly start to see an absorption channel also opening up, which is not possible to have at 0 temperature. And then eventually you get down to the room temperature case where we have a very, very small lifetime of a few femtoseconds. And the decay is now dominated by these absorption processes. Yeah, I wanted to give a brief note here of why this also is very interesting in the case of BVO. This is definitely more for the theorists in the room, but I just wanted to mention that when you're looking at electron-phonon couplings in materials, it's very common that the highest optical phonons will be the ones that most strongly affect the states in your system. So one interesting thing we're seeing here is actually, in the case of this material, there are many lower energy phonon modes that play a huge role in how this state is renormalized. That's for the real part. And for the imaginary part, these decay processes, these lower energy modes play an even more important role. This really just has to do with more that there's a lot more channels for lower energy phonons to cause a decay process to occur. But just wanted to note that like some of the previous modeling we were doing where we just look at the highest energy phonon just really aren't going to cut it for doing this analysis. So I think this really highlights the need for a first principles calculation for this type of phenomena. Okay, so yeah, that's probably enough for now. So what I wanted to emphasize is that as of very lately, we've developed a working implementation for including phonon screening in the Bethe-Salpeter equation. And this is basically the first case where we can apply this to a complex material. And it seems to be working in very interesting and nice ways. And so we can see that the binding energy for this system massively affected by the screening. And we're also even seeing spontaneous decay at 0 temperature. And so I guess, yeah, where do we go from here is basically, we're almost there, but it's a few more steps. But we'd like to try to rigorously incorporate these effects into a new absorption spectra that includes this kernel. And then, of course, look at more systems. Yeah, I don't know where I am on time, but that's what I've got. Happy for questions.